Welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last class we started module 3 relations among yarn count, yarn twist and yarn diameter. If you remember, we first started with Cochrane's theoretical concepts on how to twist a staple fiber yarn. Then we started with a simple mechanical model and we established a very important relation on packing density, yarn twist and yarn count. So, today we will start from there. When we measure twist angle, surface fiber twist angle, that is angle beta d, then it is probably not correct to consider diameter d. It is better to consider the diameter at which the axis of the surface fibers lie. So, in this image what you see is that yarn diameter is capital D. However, when we measure twist angle, then we look at the surface fibers, and that time it is better to consider diameter d prime. D prime is the diameter constituting the axis of the surface fibers. Then we talk about one ratio C subscript d, which we define by d prime by d. This C subscript d is well known as Schwarz constant. Right. So, C subscript d is equal to d prime by capital D is known as Schwarz constant. We need to find out a value for Schwarz constant. This ratio is not sufficient to determine Schwarz constant because it is very difficult to measure d prime. We need to have an expression for C subscript d Schwarz constant, so that we can determine practically and easily. So, we need to first find out an expression for that. So, that is our first aim of this lecture. For that purpose, we consider theoretical limit structure. Theoretical limit structure we talked in module 2, hexagonal packing with closest packing. So, distance between fiber h is equal to 0, and then we derived the packing density of this limit structure 0.91. This we have done in module 2. So, in this theoretical limit structure, what we see that the distance between yarn diameter and d prime is equal to d. So, that is basically the distance in case of theoretical limit structure. right. Then how we can find out now C subscript D. So, C subscript D, D prime by D, right, and we know that for theoretical limit structure D minus D prime is small d, right. So, we can write down D prime is equal to capital D minus small d by capital D. See, all are measurable quantities. Capital D yarn diameter possible to measure, small d is fiber diameter also possible to measure. So, then we can write this is equal to 1 minus small d by capital D, right. Now, the small d we would like to write as 4 T by pi into rho. This we learned in module 1. Fiber diameter is equal to 4 times square root of 4 times fiber fineness divided by pi times rho, fiber density. And what is capital D? Capital D also we learned in module 2, 4 times capital T by pi mu limit, because it is theoretical limit structure, into rho, right. So, what we see that these 4 and 4 cancel out, this pi and this pi cancel out, this rho and this rho cancel out, and then as a result we find 1 minus root over this into mu limit, right. Now, if we substitute the value of mu limit, then we obtain 1 minus by T 0.91. This ratio you will see as 1 minus 0.95 into by small t. Now, you see Schwarz constant for theoretical limit structure is equal to 1 minus 0.95, very close to 1, square root small t by capital T. Small t is fiber fineness, capital T is yarn count, index. So, both are measurable quantities, small t and capital T, so we can determine it. However, this 0.95 is very close to 1. So, we can write this expression as by small t, right. So, this is the expression for Schwarz constant in case of theoretical limit structure. What happens to practical yarn structure? In practical yarn structure, capital D is higher than that of theoretical limit structure. Also, D prime in practical yarn structure is proportionately higher than the theoretical limit structure. As a result of this, Schwarz constant remains practically same as it is in case of theoretical limit structure. So, the value of Schwarz constant does not deviate too much from in case of practical yarn structure as compared to that of in case of theoretical limit structure, right. Then we try to find out modified angle. So, angle at d prime, the surface fiber twist angle at yarn diameter d was beta subscript d. Now, what is the angle at diameter d prime? So, this angle, let us say modified angle. Modified angle, we name it as beta prime. So, tangent of beta prime is equal to pi times d prime z. Okay. Let us write this in a simple little different form, pi dz d prime by d. Now, you see what is pi dz? Pi dz is twist intensity, that is equal to kappa. So, this is equal to kappa, and what is your d prime by capital D? That is equal to Schwarz constant, C subscript capital D. So, this expression tangent of beta prime is equal to kappa multiplied by Schwarz constant, right. Then what happens to our last class expression, mu to the power 2.5 1 minus mu by 0.8 equal to q z square t to the power half. Remember this expression from previous class. Now, if we need to change this expression, we need to work with z. Why? Because this z is involved in tangent of beta prime, is not it? So, let us do that. So, let us write this expression q. Instead of z, we would like to write pi d z divided by pi d, that is basically z square and t to the power half. We do not want to change this yarn fineness. Okay. So, what we can write in the next step is q. What is pi dz? Kappa. And what is pi d? Pi times d. D is your square root of 4 times t pi mu rho, that is your d. Now, this square t to the power half. Okay. Now, so q kappa square 4t will come here and this will go into mu into rho into t to the power half, right. No, we did a mistake here. This will come here. Yes, this will come here, right. Then we can further work on this expression mu to the power 2.5 1 minus mu to the power 0.8 is equal to q, then your kappa square by 4 pi t mu rho t to the power half. Now, what is kappa? We know that tangent of beta prime is equal to kappa times Schwarz constant. Then we can substitute q tan square beta prime by Schwarz constant square 4 t mu rho t to the power half, right. Now, what is C D? C D is 1 minus, we have derived it earlier, 1 minus this, is not it? That is your C D. So, we substitute this q beta prime one minus t by t square 4 into pi. So, this t and this square root will cancel out, we will find out capital T into rho. Okay. So, we write it little different form q tan square beta prime into rho divided by 4 pi. Let us club them together into 1 by capital root T into 1 by whole square, and what is remaining is mu. Okay. So, this mu should come to the left hand side, then we will be obtaining an expression for mu. So, if it comes to the left hand side, then what we obtain is mu to the power 1.5, right, not 2.5, because this 2.5 minus 1, so 1.5. 1 minus mu so this is your left hand side. Right hand side, let us write this as a parameter capital R. We will discuss about this little later. So, Q tan square beta prime into fiber density divided by 4 pi, it is a parameter, we call this parameter R. So, this R, okay, divided by root over T into 1 minus this square, right. So, let us write it in a nice manner. So, what we obtained is mu to the power 1.5 divided by 1 minus mu cube to the whole cube R divided by root over T into 1 minus small t by t square, right. This is another important expression. In the last class we obtained one important expression, in today's class we obtain another important expression. They have tremendous application in practice. Okay. Now, before going into the application part, let us discuss a little on the character of R. What is R? R is Q tan square beta prime into fiber density by 4 pi. This 4 pi is constant and Q is a parameter, rho is constant for a given fiber and tan square beta prime. Now, it is generally seen, our practical experiences say that R is typically constant for all yarn counts and all yarn technologies. And there is an R varies for different fibers because of the involvement of rho and also other parameters. So, it is necessary for us to know the value of R for different fiber. So, fiber and R. By the way, what is the unit of R? Unit of R will be this cotton. Long staple. We generally find the value of R for cotton long staple as 2.145. Cotton fiber medium staple, the value of R we found little higher, 737. Similarly, for viscose this value we found much higher, 4.589. What is the value of R for polyester? .563, and also a value of R is reported for wool fiber. What is the value? 2.341. So, these are the values of R reported in literature. So, now finally, we will come to application point of view. Now, we have two important equations. First equation we derived in the last class, Q right. So, this was, let us write our first expression, and what is the second expression? Second expression we derived today. This is our second expression. All right. How we can use these two equations for practical application? So, this is our question. Now, when practical application comes, that time we generally know the desired yarn count. In a spinning industry, we have to produce yarn. So, generally what is the count of yarn that we have to produce? This information is generally known. So, capital T is generally known before production of yarn. Yes, which fiber I have to use, whether it is cotton or it is polyester or it is viscose. If it is cotton, then it is long staple cotton or short staple cotton, and what is its fineness. This information is also known prior to yarn manufacturing. That means, small t is also known. The moment you know about fiber, whether it is cotton fiber or polyester fiber or viscose fiber, that means you are aware about R. How? Because you know about this value. So, you know about R. That means the right hand side of second expression you will be able to calculate the value. So, you will be able to calculate the right hand side of equation 2. Then you will be able to solve this, the resulting second expression, you will be able to find mu. You can use a suitable numerical method, interval splitting method, or you can already prepare a table like in the last class we demonstrated you for solving one numerical problem. So, you will be able to find out mu. So, the moment you find out about mu, that value of mu you will substitute in left hand side of equation 1. So, the value of mu you obtain from expression 2, you will substitute that value to the left hand side of expression 1, right. Then which yarn technology you have to use? This information is also well known before yarn production. It is ring spinning technology or rotor spinning technology. So, that means the value of Q is known to you before yarn production, and value of T is also known to you. So, left hand side is known, Q is known, capital T is known. What is unknown? Only one variable, that is yarn twist Z. So, if you solve this equation, you will find out Z, yarn twist. So, that twist you have to insert to yarn. Is that clear? Let me repeat it again. So, we need to learn how we can use these two equations for practical application. When the question of yarn manufacturing comes into picture, we know about fiber fineness, we know about yarn count, and also we know about which type of fiber we have to use R. So, first we need to find out this expression, right hand side of equation 2. Then we have to solve for mu. The value of mu what we obtain, we will substitute in left hand side of equation 1. Before yarn production, Q is known, capital T is also known. So, what is unknown? Only Z. So, one expression, one unknown, you will find out the value of Z. So, that much of Z, that is yarn twist, you have to insert to the yarn. So, that is what is called suitable yarn twist. How much twist you need to insert to yarn? You remember when you started module 3, such type of question came. So, by using these two equations, we can find out how much twist is required to be inserted to yarn. Let us now solve two numerical problems. This part then will be very clear. So, we will solve first this problem. In the last class, we solved one numerical problem 1. Now, we will solve two more numerical problems. Numerical problem 2. A carded ring spun yarn of 11 tex count is prepared from long staple cotton fibers of 0.13 tex fineness. Typical practical problem. We have to produce a carded ring spun yarn, count of that yarn is given 11 tex. Which fiber I have to use? Long staple cotton fiber. What is its fineness? 0.13 tex. Estimate the packing density and diameter of this yarn, also estimate the twist required to produce this yarn, right. So, we have to solve this problem. Now, we will use these two equations for solving this problem. First, we find out this. So, we start from here. It is long staple cotton. So, what is the value of R for long staple cotton? 2.145. How I find this value? From this table, 2.145, this value. Now, what is yarn count? 11 tex. Where from I find this? Already given in this problem, 11 tex. What is fiber fineness? 0.13 x already given. So, one minus 0.13 by 11 squared. So, you can find out this, the right hand side of expression 2. What will be the value? This value will be 0.8141. Okay. So, this expression is equal to this. What is the value of mu? How you can find out? As I told you, two ways. One, you can adopt a suitable numerical method, maybe interval splitting method, or you can already prepare a table beforehand, and from that table you can find out the value of mu. So, we will start with the second case. Let us prepare a table. Table mu and mu to the power 1.5 like previous class, 1 minus mu by 0.8 cube to the power cube. If the value of mu is 0.38, you substitute mu 0.38 here and also 0.38 here, then use a simple calculator and find out this value. You will find out this value will be 3291, right. In earlier case, what was the value? The value was 8.8141 and this is 0.3291. So, mu is not equal to 0.38. Then you find out 0.39, 0.39, you substitute 0.39 here, you substitute 0.39 here, what will be the value you obtained? .3524. Is that the value? No. Then 0.40. What will be the value of mu? 0.3776. Similarly, 4051, 0.42, 4350, 0.43, 4678, 0.44, 5038, 0.45, 5435, 0.46, this value will be 5873, 0.47, this value will be 6359, 0.48, this value will be 6901, 0.49, this value will be 7507, 0.50, this value will be 0.8187. And what was earlier 0.8141. So, mu is approximately equal to 0.50. If you use a suitable numerical method, you will find out the exact value, right. So, come back to this problem. If you solve, then you will find out mu is 0.50, okay, because this expression is equal to 0.8141, and when mu is equal to 0.50, this expression becomes 0.8187, right. So, mu is roughly equal to 0.50. Okay. This value of mu now you have to substitute here. So, if you substitute mu 0.5 here and also 0.5 here, what you will obtain? You will obtain a value of this expression. What will be this expression value? Now, in the last class we solved one table. So, now if we substitute 0.50 here to the power 2.5, 1 minus by 0.8 q z square t to the power half. So, this value will be equal to 0.4094. Okay. So, 0.4094 equal to q. What is the value of q? Which yarn is this? Carded ring yarn. For carded ring yarn, what was the value of q? In the last class we discussed this value. Carded ring yarn cotton, q is 9.61 into 10 to the power minus 8. Okay. Z we need to find out. T, what is yarn count? Yarn count is given 11 ticks, right. So, 11 ticks. Now, this you will be able to solve and you will find out the value of Z. So, in this manner you will be able to solve this problem. So, Z you will find out 1133.41 twist per meter. So, basically Z is your 1133.41 meter inverse. Right. So, in this manner you will be able to find out suitable yarn twist. Would you like to do one more exercise? Let us do it. So, it will be fully clear then. Numerical problem 3, the last numerical problem of this module. Numerical problem 3. Very similar problem, very relevant for practical application. Right. A carded ring spun yarn of 29.5 text count. So, what is capital T? (29.5 text) to be produced by using medium staple cotton fiber. Medium staple cotton fiber. So, the value of R is 2.737 of 0.16 text fineness. So, fiber fineness how much twist is required to be inserted while production of this yarn? a very typical industrial problem. You need to find out Z. Okay. And the value of Q is also given, is not it? The value of Q is equal to carded ring yarn. So, 9.61 into 10 to the power minus 8 meter square right. So, this was the value of Q is also given, you need to find out Z. So, how we can find out Z? First we have to work with this expression. Okay. So, what are the values given? The value of R is given 2.737, value of capital T and also value of small t are given. What is the value of capital T? Capital T is 29.5 tex, is not it? Capital T is 29.5 tex. And what is your small t? Small t is 0.16. Okay. So, what will be this value? This value will be equal to 0.5872. Then you find out the table again, already prepared this table. Where is this value lying? 0.5872. 0.5873 is very nearby, right. So, the value of mu is 0.46. So, then we write the value of mu 0.46, all right. Then we solve our first equation, 2.5 1 minus 0.8 cube to the power 3 q z square t to the power half. If we now substitute mu 0.46 here, then we will find out this value is equal to 0.2701 is equal to q. What is the value of q here in this problem? The value of q is 9.61 into 10 to the power minus 8 z square, and what is the value of t? T is 29.5. Okay. So, if you solve, you will find out z equal to 719.38 meter inverse. So, roughly 720 turns to be inserted per meter of this yarn. So, if we summarize module 3, the target or the aim of this module was to find out a relation among yarn twist, yarn count and yarn diameter. As I told you, fiber packing density in yarn basically dictates this relationship. We started with Cochrane's theoretical model, which we did not find too much precise. Then we discussed certain empirical corrections to Cochrane's model. However, they were empirical. Thereafter, we started with a simple mechanical model and we derived two important relations. One relation was mu this relation, where mu is packing density, q is a parameter for different fiber, for different technology the values of q will be different, and we have already told about those values. Z is yarn twist, capital T is yarn fineness. Then we talked about one more equation, where mu is again packing density, r is a parameter which depends on fibers. For different fibers the values of r will be different, we have already told about those values. Capital T is yarn count, small t is fiber fineness. Then we have discussed how these two equations can be used to solve practical application. For example, typically in practice we need to know how much twist needs to be inserted. So, that is the purpose. Then first the right hand side of this expression 2 we need to be find out. Generally capital T is given, small t is given, r is also given. So, we will be able to find out this value. We will solve this and we will find out mu. That value of mu we will substitute here, we will find out this expression. Q is generally known from the table, T is already given. So, we will find out Z. So, we will find out suitable yarn twist. So, that is how these two expressions can be used in practice, and also we have shown how this expression falls in front of experimental results, and we have found out that this expression can explain the yarn twist, yarn count and yarn diameter satisfactorily. So, this completes module 3. Thank you for your attention.